One of the important processes that we have here is the convective conductive heat transport in the fluid between the fluid and the pipe wall. This depends quite a lot on the flow regime, whether this is laminar or turbulent. Laminar flow with no mixing of the fluid, and turbulent flow with full mixing of the fluid. This is governed or expressed as the Reynolds number. High Reynolds number above 2300, we assume turbulent flow. A low Reynolds number below 2300, we assume laminar flow. So the Reynolds number of 2300 for straight pipes is like a magic Reynolds number. It depends on the fluid viscosity, which again depends on the type of circulating fluid. Is this water or an antifreeze mix? And also it depends on the temperature. Now, what is important to realize is that in the design software, the critical Reynolds number 2300 is actually like a step function. So at a Reynolds of 2299, we calculate with laminar flow, whereas with a Reynolds of 2300, we calculate with turbulent flow. In real life, of course, there is no such very strong boundary, and there is more a, let's say, smooth change from laminar to turbulent. You can imagine that the pipes, for instance, are never fully straight. They move around in the borehole a little bit, causing already turbulent puffs in the pipes at lower Reynolds numbers. So this is something to be aware of in your design, that you're not very near the critical Reynolds number, because then there is a change from laminar to turbulent, which affects the design quite significantly. The design software then, the usual design software that we use in Europe, it's called Earth Energy Designer, based on the work by the Swedes in the 80s. And what we get in the results is, first of all, a graph of the base load after 50 years or 30 years for our particular system. And the base load tells us what the temperature in the ground is after we've extracted the energy, but we're not doing any capacity. So the heat pumps are actually off. Then there are two other curves, the peak load curves in cooling and the peak load curves in heating. And that peak load curve actually tells us what the fluid temperature will be once the heat pump is operating with a specific thermal capacity and for a specified number of hours continuous heat extraction or heat injection. So these are usually the boundaries for our design. We want the ground heat exchanger to be so big that it does not fall below a certain temperature after heat extraction for 50 years and delivering a specified capacity. And we do not want it to increase above a certain temperature during cooling operation. Now, as we said before, the design software calculates an average or calculates a collective borehole heat exchanger. In many instances, we have one or more boreholes connected in a collective heat exchanger, but they also have neighbors. That can be in a terraced house, your real neighbor, or in a apartment building, for instance, a number of apartments that use together one or two or three boreholes, but then other apartments have their own little array of boreholes. So then we cannot use this averaging calculation method anymore. We can calculate the thermal effect of each system, but the effects between the system has to be calculated separately, and we have a kind of iterative procedure where we do the design, calculate the thermal effects between all the different systems, and then adjust our design for those temperature effects that will give a different temperature effect between all the system, do the design calculation again, etc., until we have a stable solution. This iterative procedure, we can see here, it starts with arbitrary depths of the boreholes, then it calculates temperature effects, adjusts the depths, then other temperature effects occur, we adjust the depths until at the end, at iteration 4, we don't see any difference with the previous step anymore, and we decide that we've gotten the stable solution. Then we get in the table, you can see that for every subsystem, a different number of boreholes, a different depth, a total length, a thermal interaction between the boreholes and, let's say, the compensation factor that we've used in the design of the individual systems to account for this thermal interaction. And then on the right, we have a very small remaining thermal interaction, in this case, all positive for each subsystem. More about open and closed loop systems will be presented in Module 3, where we look in more detail in borehole heat exchangers, in Module 4, where we consider more groundwater heat exchangers, and in Module 5, where we look at horizontal ground heat exchangers.